Good morning, sir. My name is Aditya Shukla and I am from MSc Dual Degree course. Today I am going to present on superconductivity at 203 Kelvin. Okay, first let's discuss about what is superconductivity. Superconductivity are materials which offer zero resistance towards current, and they can conduct current without offering any resistance below a certain transition. Sorry, below a certain critical temperature Tc, which depends on the material and its properties. Okay. So as superconductors can allow currents to flow without any resistance to them, uh, because of that they allow a constant magnetic flux around them, and persistent currents can exist inside them in a loop. I mean, okay. So next, also superconductors are perfect diamagnets. I mean, their magnetic susceptibility is -1, and the basic reasoning behind the property of superconductivity is a strong electron-phonon coupling. I mean, it is one of the major factors which decide the superconductivity property of that material. Uh, so all this study we are doing is to search for a material that is a superconductor at room temperature. Okay, so highest yet temperature at which the superconductivity has been observed at ambient pressure is 133 K, and the BSc theory puts no limitation on TC, so there is still hope that we could find a room temperature superconductor at ambient pressure also. Metallic hydrogen can be superconductive between 100 to 240 K in theory at ambient pressures, and at higher pressures, I mean at about 500 gigapascals, in theory we, we can achieve superconductivity in metallic hydrogen between 300 to 350 Kelvin as well, but that is still in theory. Until now, the lowest TC in pure elemental metallic hydrogen that has been observed yet is only 17 Kelvin. Only the molecular hydrogen metals have shown uh, TC at between 100 to 240 K yet. So in this study, we are working with sulfur hydrides that show superconductivity at 90 gigapascals of pressure, and are expected to have a TC somewhat between 100 to 200 Kelvin. So the methodology for this study is that we chose S2S because it is relatively easy to handle and is predicted to show superconductivity at 100 gigapascals of pressure and about 80 K temperature in theory. Okay. So first, the loading. First, we loaded the sample in a DAC, and the some initial pressure increase was done at constant temperature of 200 K initially. Okay, while the pressure was increased, the Raman spectra of the sample was observed. I mean, the Raman spectra of H2S and DTS was measured as the pressure was increased. So what we observed, at around 50 gigapascals of pressure, the sample turned into a semiconductor, and at about 90 to 100 gigapascals of pressure, it is a poor metal. Okay, with a resistivity of the order of 10 to the power minus 5 ohm meter, and resistance dropped to around 10 to the power minus 7 ohm meter at 200 gigapascal pressure. Okay, so electrical measurements were done using the diamond anvil cells, and 4 probe method was used to measure the resistance of the sample. Okay, so now about the results, when cooled at about 100 gigapascal pressure, the resistance drops by 3 to 4 orders of magnitude. That indicated a transition to superconductivity. Now it was observed Tc steadily increases with pressure when temperature is around 100 Kelvin, and while for pressures above 160 gigapascal there is a sharp increase in Tc. Okay, as you can see from this graph, uh, at temperatures between 150 to 250 K there was increase in Tc with a decrease in resistance of the material. It was also found that Tc was strongly dependent on the isotope, and lowest Tc was observed for sulfur deuteride isotope of the sample. Now Tc also strongly dependent on the magnetic field. With As we increase the magnetic field from 0 Tesla to 10 Tesla, the that critical temperature Tc shifted to lower temperatures. At much higher magnetic field of a much higher magnetic field of about 70 Tesla was needed to break the superconductivity. The following graph shows the isotope effect. You can see here in the middle graph it is shown sulfur deuteride having a lower Tc than sulfur hydride at nearly the same pressures. At temperatures above 200 K, the magnetization decreased sharply, showing the onset of superconductivity. Okay. So to be exact, the onset of superconductivity was observed at about 203.5 Kelvin, as you might be able to observe from this graph. Now, talking about the properties of the new superconductor discovered in this study. So the first main property is that it is a type 2 superconductor, and the coherence length was within the limits of 2.3 nanometers and 2 nanometers, which has the same order as some other compounds like YBA2CU3O7, which had the a coherence length of 1.3 nm, and NB3SN, which had the coherence length of 3.5 nanometers. And the London penetration depth, meaning I mean how much magnetic field can penetrate inside the superconductor, was about 125 nanometers, and the intra-grain critical current density was found to be around 10 to the power 7 ampere per square centimeter. So we so as conclusion, although the experimental evidence for superconductivity has been presented here, it is still not obvious which particular compound was responsible for the high Tc. Low temperature, meaning Tc of about 80 Kelvin superconductivity relates to H2S as it is consistent with the calculations, but same is not true for higher temperatures Tc of 200 Kelvin. It is observable that hydrogen sublattice gives a major contribution towards the superconductivity. Also, the one of the noticeable properties is that the strong covalent bonding in H3S, which is in agreement that a metal with high Tc should have strong covalent bonding and high frequency modes in the phonon spectrum. Okay, so with this we can say that the particular combination of bounding type and phonon spectrum can provide a good criteria for searching for high Tc materials which are superconductors at ambient pressures. So with this I will conclude my presentation.